Okay, hello. Now we will look at reducing an image collection. So we're on slide 16. When we move there, you can see the idea is similar to in the milk example, the part where we go through all of the prices that we gathered up and we look for the smallest value. So as you heard with the milk problem, we need to get the numbers before we can summarize the numbers. So we need to do the mapping before the reducing, and this is the stage called reduce. So it's worth thinking about, and we saw it directly in on the map panel, that they don't all have the same number of items in them. One had 34 items, and the other had 83. The reason is, over in the one side, there were fewer clear images than there were in the middle part, just by chance. So in one place, at one pixel, the stack might be 15 items high, or maybe somewhere else in the same area, according to the same criteria, it might be 200,000 items high. And so we would like to have some operation to allow us to talk about what's the summary set of statistics for this. And Earth Engine provides some useful, really useful ways of looking at it. So you can do with this syntax, you can say, I have my set called L5EVI images. That's what was produced at the end of F4.0B. I want to do a reduction, and the reduction is called this, mean. And the way we say it is we say ee.reducer.mean with the two parentheses and the parentheses outside. And then we can print it out. And that will basically, this line here creates one layer from at every pixel. It creates one value at every pixel, which is the average value at every pixel, whether it's 15 items, an average of 15 items, or an average of 2,000 items. We then can draw the L5 EVI on the screen with map.add layer between a range of -1 and 2 in this case, and make some little palette, and then put a label in the on the map panel so that we can see where it is. And so let's go do it. We will go here now to F4.0C. And F4.0C looks just like F4.0B, which looks just like F4.0A, but it has some more stuff down at the bottom. So you can see there's the end of F4.0B right there. And now here's that reduce that you just saw on the page. Reduce with the mean, print it out, send it out to map.add layer. We can also see the example of the median. We can ask for the 50th percentile value is what the median is, so the middle value. The mean value might be thrown off by some really large numbers, for example. And so let's take a look. So when we run this, I expect to see one image drawn here, I guess one image here, one image here, and one image here. So I expect to see 3 things over in my data layer. Good. Let's go down to take a look at them. What you can do, you can click on this, checkbox, or if you want, I discovered you could type the number 3. I'm typing 3, 3, 3, 3, 3, 3, and turn off number 1, 2, 3, and turn it on and off. If you fall off the edge of this window all the time, you can type that little lock button and then it will stay on, which is really nice. So you can type 3 to turn it off. Whoop, type 2, and now I have just the bottom one. That's the first thing that we saw. And now when we look closer, we can see that there really was a stack here. It looks like you're looking from above, looking down on some images. You can see here's the corner of one, the corner of another, and those are just the way that the data gets brought in. Could be that if we go here, we can also see see the edges of this data. So that's pretty neat. So it reminds me that there is this stack of data. Now, if we turn on the mean, I think I don't expect to see something that looks so much like a stack. I'll zoom in a little bit and see, I don't expect to see something that looks so much like the mean of a lot of layers, or a stack of layers, sorry. So I'll leave that on for a second, turn on the mean, and it will draw. Now what it's doing, again, is it's taking the average value at every pixel going all the way through. Then it will draw the mean value for us on the page. Now you remember the mean value, I said, oh, we'll make a little palette. So the palette goes from red to white to green, if I remember right, and that draws the mean EVI. Now I mentioned, and you've probably seen this before, that that average values can be really thrown off. If you're looking for the average value, the average income of all the people in a town might be a very large number if there are a few very wealthy people. And so that might or might not be the representation of that area that you're looking for. Here in this case, we can see a lot of variability. I'll try zooming in. I guess this is over the water. I don't really very much want to be over water. So I'll move back and come in over here where it's maybe not so noisy. So we'll go here, and now I'll click on the inspector just while we wait for it to draw, and we can see, okay, at that pixel, what did we have? At that pixel, we had a series of images. Now you remember that we mapped the EVI function over it. So all the numbers were here. They were between 1 and 2, or 0 and 3, actually. Then we had one crazy high, very high number, 8.489, and one very low number, whatever that is, -17 for some reason. There probably was a cloud that got through, or a cloud shadow that got through and threw off, kind of broke the number on that day. So the mean might not be the best representation of this. It's probably pulled down a lot. There are a lot of images. There's 70 some images. So this one might not have pulled it down so much, but it's probably lower than what a typical number is. If we want to say a typical number is like between 0 and 1. Well, the mean here is lower than it maybe would be, 0.839, and the median is a little higher. The median is the typical value. I always say the word typical when I say median, which is the 50th percentile number. So you might wonder, why did we draw the palette with this particular range of -1 to 2? And the reason is, when we drew it with from -1 to 1, some numbers just didn't look very good. So we made the number higher, even though the range really should be -1 to 1. Some of them just were strange, and we wanted to be able to show that variability instead of having it just blank out to be white or blank out to be black. So this was just in order to draw it well. And really, I believe, if I remember right, it's the mean value is the one that's weird. The median value has a little different type of smoothing associated with it that gets rid of a whole lot of the individual noisy values. And I think the way that this has been described to me, you would say, why is this thing so noisy? Well, there are a lot, if I zoom in a lot further, there are a lot of pixels here on the page. If you were to count all the way across, here's 5 pixels here, there's 10, so there's 20, there's 30, there's 40, let's say there's 70 pixels in that direction, and there's, say, 15 in that direction. So that is 1,000 pixels on the page, and that is a lot. So if only 20 of them is off, it's going to look really weird, even if 20 out of 1,000 is only a couple percent. And so it's aggravating to have all of this noise, but it's because there are so many numbers being drawn on the page. And I think psychologically, our eyes are drawn to the parts that are the shiniest or the most unusual. And it's hard not to look at all this red and see the green that is really behind it. And so that is a great advantage of the median. Here you see I have it able to be slid back and forth. You have the median, which isn't perfect, but it's different. And so maybe in one case, it might be useful. In another case, it might not be so useful. So for me, I tend to like the median. That can be pretty neat, especially for noisy data and especially for satellite data, because we have, even if we spend a lot of time or a lot of energy working on getting rid of clouds, there are always, it seems, 1% of the 1% of any set of values are just bad. And so drawing it without any further treatment often draws my eyes to the places that are bad. And treating them with an average does an okay job, but it can be really thrown off by outliers. So these statistical, the foundations of statistics that you hear about if you take a class really come into play in my experience with remote sensing. In a class, they will say, well, be careful of the average because it can be thrown off by big numbers or small numbers. That's true, but I don't think about it very often, but when I think about it all the time when I do remote sensing data, and that's because some of the numbers, not a lot of them, but just some of them are really wrong, and we don't want to draw the wrong conclusion from these numbers. So I'll do one last thing, which is I'm going to zoom in on just one of these numbers, and let's see if we can understand why this number is so weird. The palette went from, in this case, from red to white to green. So the red numbers are very low. Why is this number so low? Well, here it is. We can see there's one number was extremely low, and it sort of broke the whole thing. I say broke in the sense of if I want something to be clean. But here, if I look for just the median value, it's going to be some small number, right? And so that median value, there's no noise there. So I say broken, not exactly right to say broken, because this might be a way to get rid of the last little bit of clouds. I could say, I want to see the median value minus the mean value. And where the difference between these two is large, those are places where we have a problem. There might be some places that naturally have a very low value. If they always consistently have a very low value, then the mean and the median would be the same, but a low number. In the case where just one number was pulling it down, and let's go click on some other red one, see if that theory is the same. Yeah, there's another one where just the one number is pulling the whole thing down. And over here for this one in the inspector, we can see the mean value is very low, negative 1.35. And the median is there. So if we were to try to subtract these two numbers from each other using the subtract command, you would be able to make a new image that would see that. And so why don't we do that? Well, I don't want to do it in my own checkpoint because that will break it. I might accidentally hit save. You can do that same type of thing. And so I said the word broke, but I only meant in a numerical sense that it pulled the number down a lot. And so the appropriate time to use this, I'm a big believer that there's no perfect answer in remote sensing. You have a set of tools and you have a problem to solve. And so in this case, I would say the mean shouldn't be used directly because the mean is susceptible in this particular data set. It's susceptible to having some numbers that are not representative of the whole data set. However, the mean could be really useful for finding those pixels that have that particular characteristic by having one or maybe two numbers that are really low and then we could maybe go and screen them out. You could imagine doing some sort of test to get rid of numbers that are less than 1. And then this series actually would go back to being great. And maybe the mean would be a good number in that smaller data set. So, if we click in a normal spot, what I'd call a normal spot, these numbers are very close. So 1.14, 1.11, maybe for some types of projects that matters, and other types it doesn't matter. We can guess which ones will be close by looking for colors that are the same. When I move back and forth, I'm seeing this one here. These numbers seem pretty similar to each other. 0.82 and 0.64. I guess I figured they would be closer than that, but that's how we could use it. I tend to like the median a lot, and we'll talk about that in just a moment. So I'm going to now, just to finish this section, I will finish, and we will now go look at some bonus material from the next chapter, from 4.1.